Okay, and I'm happy to introduce the second talk of this session that will be done by Lennart Döppenschmitt from University of Toronto, and who will talk about the moduli space of generalized Kähler metrics. Lennart, can you? Okay, you're here.
Can you hear me?
Yes.
Is the other slides big enough on the screen, because it's very minor on my screen?
It's very small. Yeah, most of our screen is white.
I see it on the left corner, yeah, and it's less than a quarter of my screen.
Second. How about this?
Yes.
It looks better. Yes. Perfect.
Okay.
Perfect. Yeah.
Let me go to full screen. Yes. And the audio, can you all hear me?
Yes, it's a bit quiet, but that's okay.
A bit quiet. I can turn it up a bit. Okay, this might be better.
Yes, it is better. Mm-hmm.
All right. So 25 minutes. Let's go. Thank you for the invitation to speak on this conference. I'm going to be talking about the moduli space of generalized Kähler metrics. This is my PhD project, and it's actually joined, therefore, with my advisor, Marco Gualtieri. In this talk, I'll be, can you see the second slide?
No, we see the message about sharing your screen. Ask him to tap. Yeah.
Okay.
Yeah.
Okay.
Now we can see.
I hope this doesn't happen again. All right.
Okay.
So in this talk, I'll be going over the background first, and then I'll describe two observations. The first one is by Donaldson, and the second one by Fine. That both relate. That both concern classical Kähler theory. Afterwards, I'll unify these approaches, and then generalize to the generalized Kähler structures. So let's start with the background. For the entire talk, I'll be fixing a compact complex manifold, which denote by X, and this is going to be of dimension 2n for the entire talk. A symplectic structure on this manifold is a true form which is close and degenerate and non-degenerate, and compatible with I means that it meets either of these two conditions. So one can either say that it's of type 1,1 with respect to the complex structure I, and that would mean that the anti-commutator of omega and I vanishes. Or one could also say equivalently that the combination omega and I defines a Riemannian metric. In this case, we say that they're compatible, and such a triple of I, omega, and G, we call a Kähler structure, and this is what we're interested in. So locally, we can describe the Kähler metric by a real valued function, which is called the Kähler potential. So on any open, omega is going to be del bar del of phi. And this is very nice for local computations because it simplifies the degrees of freedom. So once we fix the complex data, which is the complex manifold, the background, then this is the real data that determines the Kähler structure. The only problem is that this data is not globally defined. So we cannot have a global Kähler potential. And the question that I'm going to be addressing in this talk in general is that what are the possible Kähler forms, the symplectic structures that we can find in a fixed complex background, which are compatible with the background. Okay, let's start with Donaldson's approach. Donaldson made the following observation, that if we fix an open set in X, and we assume that it is that the first bit number vanishes, then what he does is he considers maps between symplectic manifolds. In this case, it's a very specific setup. Namely, the target is the holomorphic cotangent of U with the canonical symplectic structure omega naught. And he considers those maps, which are actually graphs of holomorphic one forms. So this means we can write alpha as alpha R plus I alpha I. And then he imposes in this mapping space a certain condition. So he wants to find a sublocus of those maps that satisfy the so-called Lagrangian symplectic condition. This means we require that it's Lagrangian with respect to the imaginary part of omega naught and symplectic with respect to the real part. Now, if you look at what this means explicitly, then we see that because H1U is 0, for the imaginary part, this simply means that it is closed, therefore exact, and therefore it is d of a function phi, where phi is a real valued function on U. Well, if we go further, we know that the imaginary part of alpha I is precisely this expression, which we found up here to be d phi. And the 1, 0 part of d is precisely del. So this means that we can infer that alpha is precisely 2I del of phi. Now we use the second condition, and this means that the pullback of the real part of omega naught, which is now in the entire part because the imaginary part vanishes, is d alpha. Now, if we insert this equality that we just found, then we see that this is precisely del bar del phi. And by assumption this is symplectic, this is non-degenerate, meaning that this is a Kähler potential on U. So what this computation really shows is that locally on U, we have a one-to-one correspondence between the L-as graphs in T star U, the holomorphic cotension bundle, and Kähler potentials on U modulo R. As I said, that this is a local picture. So I'm not quite done with this. One could say this is a story with a twist, because if we do this globally, there's one big problem. The Kähler form that we just described as del del bar of phi is exact, but if X is compact and omega is globally exact, this is a problem because it can't be non-degenerate if it has 0 volume globally. So what we do is we can only do this locally, which we just did. So let's say that A alpha are primitives of omega locally. And the problem that they don't agree globally can be said that their difference A beta minus A alpha does not vanish on the intersections. So this is the left-hand side is the picture that I described to you with Donald's perspective. And what we can do is we can change this picture by an isomorphism on T star U alpha, where we just shift the entire cotangent bundle precisely by the value of A alpha. What this gives us is this phi alpha, which is an isomorphism of the symplectic manifold underlying T star U alpha. And this is exactly a symplectic morphism if we add to the canonical symplectic holomorphic symplectic structure this term of D alpha, dA alpha. And you can also see that the section which encodes exactly the Kähler potential corresponds to the identity section on the right-hand side, epsilon. So this is really an isomorphism of symplectic bundles with this section. Now, the nice thing about this formulation is now that the difference of the alphas does vanish. So we are able to take those those local patches and glue them together by the identity map. And the holomorphic symplectic structure together with this deformation will glue to globally to give us this bundle. And this is a holomorphic symplectic bundle over X with a section. Let's talk about Fine's approach. So what Fine does is he considers the Kähler structure or the Kähler theory as a gauge theoretic theory. So what he does is he starts with a complex Hermitian line bundle U, and he considers the space of all connections. But because we want to talk about symplectic structures, we require that the curvature, which I denote here by omega sub nubla, is symplectic. And even further, we can refine this picture by saying that we want to particularly look at the connections which have symplectic curvature, which are also compatible with the complex structure. So we call this S11. The complex line bundle U has a gauge group tau, which is just maps in S1. And naturally, this acts also on the connections. So what we can see is that the structure that S has is a naturally complex structure because connections are affine over one forms, and every complex structure induces a complex structure I star on the one forms. And we can also say that S has the following symplectic structure, which is given by this expression. So in total, what this means is that tau acts Hamiltonianly on S11 by Kähler isometries. And whenever you give a symplectic geometer a Hamiltonian group action with an equivariant moment map, which is given by this expression, then it's very natural to take the quotient. And the benefit of this is that the quotient will inherit a Kähler structure. But this is not the end of the picture, because what Fine really is interested in, I switched the slides. So what Fine really is interested in is expressing the Calabi conjecture in this setup. As you can see that the moment
can you try again? Can you try again? I think the slide didn't change for us.
Oh, okay, now it does.
Yeah.
Okay. One thing that Fine does with the setup is he's able to interpret the Calabi conjecture, because as you can see from the previous slide, the moment map takes values precisely in the top forms, the two end forms of on X. And so if we take the symplectic reduction, then what we do first is restrict to a level set. But restricting to a level set is precisely singling out those curvatures, those connections with curvature that have a fixed volume form. And the Calabi conjecture is precisely about finding a Kähler form in a class with the prescribed volume form. The only problem with this is, though, that the moment map is equivariant. So this means as much as we move around in the orbit, we will never change the volume form of the Kähler form that we obtain. So we have to act by something else, and this is precisely done by tau c. So as I said, the action preserves the complex structure on S11, so we can complexify the group tau. So then we get that tau c acts locally holomorphic on S11, and we're able to change the value of the moment map on the connection. So then he arrives at the following lemma, which is that for any nabla knot in S11, the tau c orbit subjects via the moment map, which gives us the Kähler form to the corresponding pre-quantum data, onto the class C1, onto the class of Kähler metrics in the fixed class C1 of U. Okay, and now the goal is to unify those two pictures. I'm really not happy with the slides because it doesn't switch.
Yeah, we still see slide 9.
Yeah. Well, 1 second. Okay, now it's a cable connection, not a Wi-Fi connection, so it might be more stable. It means that you have to see the ugly tools, but that's okay. So as I said, now we're talking about the unification of these both. So the first is just a new perspective on what I just told you before about Donaldson's perspective. So I told you absolutely the truth. The only thing is I didn't tell you all the things that we can say about this. So for one is that the cotension bundle, T star X, is not just the cotension bundle, but it actually is a groupoid. And because it has a symplectic structure, we can actually say that it's a holomorphic symplectic groupoid. And this goes even further, because we can say that it's the Weinstein groupoid, the integration of the zero Poisson holomorphic Poisson structure on X. So because this is a groupoid and Z is precisely built by local pieces of the groupoid T star X, we can use the multiplication locally to define an action of the groupoid T star X on the Z space that we built previously. So this means, to summarize, the Z space that we built, which carries the data of the holomorphic, of the bisection which encodes the Kähler data, is precisely a holomorphic symplectic groupoid principal bundle for T star X. And because it's going from X to X, we can also view this as a Morita equivalence from X to itself of the holomorphic zero Poisson structure. Now I'll explain more about this later, but we can say that the classes, the isomorphism class of this bundle is precisely controlled by classes in the group the quantity group H1 with the sheaf of closed holomorphic one forms. So if we glue them, these are precisely the gluing information that we need to glue Z out of pieces of T star X. But now notice that this is precisely the same class that omega is in. So this means that this background, this holomorphic symplectic groupoid principal bundle is the background which encodes the Kähler class, and L is the bisection, the smooth datum which is missing in the picture to define the Kähler metric. Now, how can we unify this with fine? Well, fine is talking about connections on a Hermitian bundle U, and I call this the bundlification because what we do is we interpret the affine structure, of the unitary connections over one forms as bisections of the Z space. So if we have the bundle U and we take any arbitrary connection on this and the curvature, and then they form magnetically the holomorphic cotangent with this curvature, then we get a Z bundle, a Z space in this class. It'll depend on which connection we choose, but this is irrelevant because they're all holomorphically symplectomorphic. So this means we can interpret everything that fine does in terms of groupoid data. So instead of unitary connections over one forms, we take bisections of Z, which are affine over bisections of T star X. And here we see that because Z is an affine bundle over T star X, this affine structure induces the affine structure on the bisections. So for any connection, we have a bisection L sub nabla. And if we want to refine to the space of S11, which has the connections that are compatible and with I and also symplectic, then we need to look at the LS bisections. But this is precisely what Donaldson did. So Donaldson looked at the LS graphs of one forms in the Z space. And instead of taking the curvature of the connection to get the Kähler form, what we do is we pull back by this connection omega. So this is these two things shouldn't be nothing new. It's precisely what Donaldson does. It's Donaldson's perspective encoded in Fine's picture. And then Fine also has the that's the whole point of what Fine does. It's the gauge approach. So he needs a gauge group that acts. And in the he talks about the maps to from X to S1. But in the groupoid picture, it is really the Bohr-Sommerfeld Lagrangians in T star X. To continue the story, the next step what Fine does is he complexifies the group because he wants to interpret the Calabi conjecture. So he has to artificially complexify the group and then in a very complicated manner determine what the action of this complexified group is. But in this picture, one benefit is that the complexification naturally arises because if we have Lagrangian bisections in T star X, the complexification is simply given by adding a unitary line bundle on L. So then if this unitary line bundle is flat, this means we get a brane, a Lagrangian brane in T star X, which perfectly continues the story of what Charlotte was saying earlier with Lagrangian brane bisections, Lagrangian branes. In our case, the additional requirement is that we want this to actually also be a bisection of the groupoid bundle. Now, before I can wrap this first part up, we can also notice that the Z space, which is an affine bundle and not holomorphically isomorphic to T star X, is, however, smoothly symplectomorphic to T star X. So this means the underlying smooth spaces are diffeomorphic. So this means we can actually view the Z space as a space-filling brane if we equip it with a unitary line bundle. And the overall goal is to encode Kähler data. So how do we recover this? It turns out that the Kähler form in this picture is now recovered as the curvature of the difference of these brane bisections, branes. One is a bisection, the other one is space filling. So many words. So when we take the difference, this means we really take the difference of the unitary line bundles above them. So we tensor U0 with U0 and subtract the connections. And we view this as a new Lagrangian brane bisection on the intersection Z intersected L. And the curvature of this is precisely the curvature of the previous connection and the pullback of capital omega by the brane by the Lagrangian bisection L. Now to the generalization. Well, this all works really well for Kähler geometry, but you might wonder what's the fuss about all this if everything just worked for Kähler geometry just fine. Well, the reason is that I'm interested in generalization of this. And this was most recently formulated in a really nice way, which fits in this picture by Francis Bishop, Marco Gualtieri, and Maxime Zevzin. So they say that a degenerate GK structure of symplectic type, this is just a specific version of a GK structure, which is usually given by the quadruple I plus I minus Q and F, is equivalent to the data of a symplectic Morita equivalence, which is this Z, together with a brane bisection L. And this is a Morita equivalence between two holomorphic Poisson structures, which are given by sigma plus and sigma minus. So this means,
Lennart?
Yes.
A 5-minute warning.
Okay. So this means that secretly, this has been the goal the entire way. The reason that we reformulated the classical pictures of Donaldson and Fine is because we wanted to soup this up to make it compatible with the generalization. And the these homomorphic Poisson structures have an underlying common imaginary part, capital Q, which is a real Poisson structure, an M, the underlying smooth manifold. And the symplectic structure F can be retained by the pullback of omega by L. So in particular, if you view this with a kind of biased view, this picture on the right-hand side, you can see that this is a groupoid. This is the Weinstein groupoid integrating sigma minus on X minus. Then that this groupoid, because of reasons that I'm going into more detail later, because this is the Morita self-equivalence of X minus, we have a composition, we have an action of sigma minus on Z. So this means that we can view this in particular as a principal bundle of this groupoid over X plus. And now the question is, what is the class of this? And just as I told you earlier, that the class of T star X groupoid bundles is given by a certain cohomology class in the Czech cohomology, we can now say that the principal bundles for this groupoid over X plus is given by a class in a Czech cohomology with a sheaf of holomorphic Lagrangian bisections of sigma minus. I'll talk more about this later, but this is in part 2. But this is precisely the generalization of the classical picture. So now the reason that I need the Q is because, again, I want to view Z as a brane inside this, this now smooth groupoid, smooth symplectic groupoid over M. And because we said previously that L is a bisection of Z, if they're smoothly diffeomorphic, then this means that, the imaginary parts are smoothly diffeomorphic. This means that the brane bisection might also be considered in here. So again, as the previous, similar to the previous story, we're able to talk about two branes sitting inside sigma omega, the imaginary part of the Weinstein groupoid of the imaginary Poisson structure. Then we can say that we cover exactly the datum that we need, the form F by the difference of Z and L. And now the final lemma, which I'm going to state today, in the first part, is a generalization of what Fine said about the complexified group orbit. Namely, if we fix any Lagrangian brane bisection LU nabla in this groupoid, then the map that sends L to the curvature of the difference with Z is a surjection from its group orbit of Borshammerfeld Lagrangian brane bisections onto the space of generalized Kähler metrics or Kähler structures in this fixed class, which Z determines. The reason that I have to intersect with LBB is an open condition. If you flow, so since this is a complexification of a real action, there might arise a problem that we leave. If you flow this for too long, then we might leave an open locus. But other than that, and we can just say this in simple words, is that we can reach every single generalized Kähler metric of the generative sublective type by flowing along this LBB orbit, as long as we fix the class of Z. These are the references I used, the papers I mentioned. And that's it for the first part. Thank you for your attention.
Thank you very much, Lennart. Wonderful. So let's all give a round of emoji applause to Lennart.
Thanks, Lennart.
I will voice it. Great.